Hello friends, I welcome you in lecture number 2 on complex differentiation. In previous lecture we have understood about complex numbers and now we are familiar with complex numbers and algebra of complex numbers, that is how we can have addition of complex numbers, product of complex numbers, division of complex number, etc. Today we are going to talk about complex functions. So what is meaning of complex function? You have studied about function of real variable denoted by f of x. This we have studied up to our school level when we write that f is a function denoted by fx, then here x can take any value from this set of real numbers. For example, if we consider fx equal to say x square, then this is function of real variable. We say that x is a real variable. And suppose we denote by capital C the set of all complex numbers. We have seen about complex numbers, so I denote by capital C the set of all complex numbers. Here x and y are real numbers, and now we know that I is square root of minus 1. So if we consider any complex number in this set, then we can say that suppose z is in this set, say capital C, then we will say that z is a complex variable. If z can take any value, or if z can take any complex number as its value, then we say that z is a complex variable. And if we consider function of complex number denoted by f of z, then we can say that this is a complex function. So this f of z is a complex function and its domain is some set D which is subset of the set of all complex numbers. For example, if I consider f of z equal to say z square, then this function is defined for all values of complex variable z. Therefore here domain of this function is D equal to, it is defined for every complex number, so domain is the whole set of complex numbers. But suppose I consider f of z equal to say 1 by z, then this is defined for all complex numbers except z equal to 0. So here domain will be set of all complex numbers and we exclude z equal to 0. So definition of complex function is similar to the definition of real function. Complex function is that function which is defined on some domain D, where D is a subset of set of all complex numbers, and real function is function which is defined on the domain D, where D is a subset of set of all real numbers. And whenever we have complex function, suppose I consider f of z equal to say z plus 1, then if I consider z equal to say x plus iy, then I will put z equal to x plus iy here. So f of z becomes x plus iy, z is x plus iy plus 1, and this we can rewrite as x plus 1 plus I times y. Now we know that this f is a complex function, so whenever I consider any particular value of z from the set of all complex numbers, f of z is also a complex number. So we can see f of z is a complex number whose real part is x plus 1, that is real part of f of z, and imaginary part is y. So every complex number can be written in this form: real part of f of z plus I times imaginary part of f of z by taking z equal to x plus y in the given formula of function. For example, if we consider f of z equal to z square, and if we want to write down f of z equal to z square in this form, then we consider z equal to x plus iy in the formula of function. So if I take z equal to x plus iy, then I will have f of z equal to square of x plus iy, and this I can simplify using the formula of square of a plus b, that is a square plus 2 times a into b. Here we consider a equal to x and b equal to iy, plus b square, that is square of I into y, and this we can rewrite as x square plus I into 2xy plus here square of I times square of y. Now we know that I square is nothing but minus 1. So if I take I square equal to minus 1, then I will have x square plus I times 2xy minus y square. And if I consider those terms which are not multiplied with I, and if I consider the term multiplied with I, then I have written my complex function in this form. Suppose I consider this is equal to say u plus iv. Because it is a complex number, we assume that this is equal to say u plus iv, and if we compare, then we see that u is equal to x square minus y square, which is nothing but real part of function f of z, and v equal to 2xy, and it is imaginary part of f of z. So what we have written here, we have written our function f of z equal to z square in this form. U, which is function of two variables, say x and y, plus I times v as a function of two variables 2xy. So this is for f of z equal to z square, and it is in general we can write every complex function in this form u plus iv, where u and v are functions of two real variables x and y. U is real part of f of z and v is imaginary part of f of z. So this we will require. Here also you can see u is x plus 1 and v equal to y. So this we will require, that how to find out real and imaginary parts of given complex function, or how we can express given complex function in this form u plus I into v. So for that, what we have done, we consider z equal to x plus iy in the formula of given function, and we try to write down our simplification in this form, something plus I into something, and we can easily find out real and imaginary parts of given complex function. So this we will require in the discussion of differentiability of complex function. You must be able to decide the real and imaginary parts of given complex function. For example, if I consider f of z equal to say z into real part of z, then I start by considering z equal to x plus iy, then I will put z equal to x plus iy in the right hand side here. So this will give me x plus iy times real part of x plus iy. This we can again rewrite as x plus iy. Real part of x plus iy is x, and then I multiply this bracket by x, and I will have x square plus I times x into y. And if we compare this with u plus iv, suppose this is equal to u plus iv, then u is x square and v equal to x into y. So these are the real and imaginary parts of this function z times real part of z. And this is very much important in the definition or in the method of finding derivatives of complex functions. So you must be familiar that how we can obtain real and imaginary parts of given complex function. Sometimes we will require to write our complex function in polar form also. We have discussed about polar coordinates, that if we have z equal to x plus iy, and if we take x equal to r cos theta and y equal to r sin theta, then by taking this x and y here, we are able to write our complex variable into polar form as z equal to r into cos theta plus I sin theta. So sometimes we will use this polar form of complex variable to write down our function in that form. Suppose I consider z equal to r into cos theta plus I sin theta here, then I will obtain 1 divided by r into cos theta plus I sin theta. Now I want to write down f of z in this form, u plus I into something. So I will multiply this numerator by conjugate of this. Conjugate of cos theta plus I sin theta is cos theta minus I sin theta, and here also we have to multiply by cos theta minus I sin theta. Here I write cos theta minus I sin theta. Then we keep this numerator as it is, cos theta minus I sin theta as it is, and here we can apply that formula, that a plus b into a minus b equal to a square minus b square. So a is cos theta, so we have cos square theta, minus b is I sin theta, square of I sin theta is I square times sin square theta. And now if we simplify this is cos theta minus I sin theta, here r as it is. Now we know that I square is minus 1, therefore we will have cos square theta plus sin square theta using I square equal to minus 1, and we know that cos square plus sin square is 1, therefore we are left with cos theta minus I sin theta divided by r, and therefore we can rewrite this as cos theta divided by r plus I times minus sin theta divided by r. And if we compare with say u plus iv, then we find that real part is cos theta divided by r and imaginary part is v equal to minus sin theta divided by r. So sometimes we will require to find out real and imaginary parts of given complex function in terms of polar coordinates also. Here u and v are expressed in terms of polar coordinates r and theta. So this will also be required, that how we can write down f of z as u plus iv, where sometimes we find u and v as functions of x and y, and sometimes we will require u and v as a function of r and theta for determining the differentiability of given complex function. Now to check the differentiability of complex function, we will require knowledge of partial derivatives. We have seen that real and imaginary parts of given complex function are functions of two variables, x and y. U is function of x and y, v is function of x and y. So whenever we have function of more than one variable, we can find out partial derivatives with respect to given variables. Here u is function of x and y, so we have two partial derivatives of first order denoted by del u by del x and del u by del y, or we can use these notations also. Similarly, for v also we can have two partial derivatives of first order denoted by vx and vy. So you must be familiar that how we can obtain the partial derivatives of function of more than one variable, which you have studied in the topic of partial derivatives in semester 1. So we will require this knowledge of partial derivatives also in determining the differentiability of complex function. And in next lecture we will see that how we can check whether given function is differentiable or not. And this is all about this session. I hope you like it. Thanks for watching.